Welcome, welcome to Iron Beetle, a show where we where we discuss compaction. So, in general, Iron Beetle is a show about TagaBeetle, the financial accounting database implemented in Zig, which, besides being implemented in Zig, has a bunch of fairly interesting properties, like being super reliable, coming with deterministic simulator, not locating memory at startup, and whatnot. But for the last many episodes, we kind of like being in and out of compaction. So remember, we had super long series where we discussed one implementation of compaction, then we quickly finished that off and did a round of overviews about TagaBeetle. And now we are at the compaction again, because since last time I've refactored the code quite a bit, compressed it a little bit, like there is like 500 lines less of code in compaction, and hopefully simplified it. So hopefully today is like really the last day of compaction. So let's get started. Okay. Oh dear. Oh dear. I've lost my terminal. Okay, I now have my terminal, but I've lost my Twitch. Let me regain that thing. No, it doesn't work. Okay. Okay, should be good now. And let's jump right in. So, compaction. I think I might want to bump this a little bit. Compaction. Compaction. Okay, I guess this is a little bit outdated. Let me refresh this. Okay, yeah, compaction dispatch. So, as a reminder and as an overview, now the entire flow of compaction is in this compaction dispatch function, which is pretty long. Line numbers, toggle line. Okay, so we don't see this, so this is line 970. and the next one is 192. So like 200 lines of code or something like that. Okay, so this single function runs the entire compaction. So the job of this function is to take one table from level A, a bunch of tables from level B, read them all from disk, merge their values, and produce a new series of table for level B. And this like function is actually paste. So we want to do the work not in one go, but to split it across 16 bits. The way we do this is that before we start compacting the thing, using metadata in the table, we compute the total amount of values, then divide the total amount of values by 16, like roughly, and for each bit, we just, process 1/16 of our work and then say, hey, we are done. So how does this work? This works through a series of ring buffers. So in general, our job is to read level A and read level B. That means that we need to read index table, and then we need to index block, and then we need to read each of the value blocks. And we put all the index blocks and all the values blocks into those ring buffers. And if, for example, if we want to read a value block, then what we do is that we look at the latest read index block, and if it is not ready, so if it is just read index block, then we are skipping the work. But if it was fully read, so we get read index block done, then we actually go and start. So we add a value block to the queue of value blocks, and then we start the read of value blocks. And this is where we started last time. So we finished read level A index block, read level B index block, read level A value block, and read level B value block. Okay, so now comes the actual work of merging the data. And okay, so let's see. Okay, so this is where the work happens. We run compaction merge, and now let's figure out what are prerequisites to get to this stage. Well, let's unwrap this whole bunch of ifs at the same time. So first thing, compaction table builder, state, index, and data block. So what the hell is this thing? If you remember, at the start of this function, we started with acquiring blocks from a shared block pool. Shared means that it is shared across all compactions. Acquiring blocks and given those blocks to table builder. So table builder is a thing which incrementally constructs the table, and table builder needs two in-memory blocks for working. One block holds the current in progress index block, and one block holds the current in progress value block. So to actually proceed, and when we merge things, we write them out directly to the table builder. So we could only proceed to the merge if the table builder actually has this index and data block. So that is the outer if. And when it is not the case, when it is the case where there isn't a block in the table builder. Well, because this is the first thing that we do in this loop, this necessarily means that we go to this case. So it could only be the case that we don't have table builder blocks if we are already writing something out. So what happens is that we started compaction, we allocated some blocks for a table builder, we filled the entire block, and we scheduled this block for being written. And this is the point where we have run out of blocks. So we have run out of blocks, but we are not stuck. We are not deadlocked, because there is a block which is currently written out, and once it is done, the block will be released and we'll be able to use it for merging further. Okay, so we have block. Now, what else could happen? Well, it could be the case that we've actually already done our entire share of work. Well, not our entire share of work, but actually we've merged everything there was to merge on level A and level B. We've read to the end of level A and to the left of level B, and this is like level A exhausted and level B exhausted. So, the condition for stuff being exhausted is when our ring buffers, our queues are empty. So if both of our queues are empty, then we are exhausted. Here you may ask that, hey, kind of like, does it work? Because, well, when we start compacting, our queues are empty. And what if it so happened that we weren't able to fill the queues simply because we've run out of blocks? That cannot be the case, because the first thing we do is that we allocate blocks for reading from the index block and from a value block. So kind of like we size the number of blocks we have in a pool such that the blocks are impossible. And that means that we actually could not get to this condition because we didn't have a block, because that would mean that we could hit a deadlock. So it is indeed true that the level is exhausted only when the both queues are empty. For level A, it is kind of like the same, except that there is also the case that level A might not actually have on-disk table, it might be just the in-memory array, in which case we separately track this level A immutable stage exhausted. So, okay, let's go next. We know that we have output block, so we actually can do the merge, and we know that it's not true that both levels are exhausted. One might be exhausted, but not both. Okay, so let me do a sip of tea. If the level is not exhausted, this doesn't actually mean that we can immediately start merging values from this level, because it could be the case that there is a value block in this queue, but that block is in the stage read value. So it's not read value done, it is read value, which means that there is an in-flight read which fills the block from disk at this very moment. So we need to check that the blocks we want to merge are actually ready. So let's see what level ready means. Level B ready means. Level B ready means that we have some value block there, and the block is in read value done. And for level A, similarly, we have a block and it is read value block done, or we are actually just an immutable table. So, okay. If kind of like level A is exhausted already and level B is exhausted already, then we can proceed as long as we have space in the table builder. So this is confusing. This condition checks that the table builder actually has a value block, but this value block might be like completely full. So we additionally need to check that it is not full. Okay, anyway, if everything here is true, then we can actually do the merge work. Now, merge is CPU intensive work. And in the future, actually, we probably would want to offload merging to a CPU pool. We don't have the CPU pool, but we already model it in the code. And we do this using our pool abstraction. So a reminder, pool is a resource pool which is shared across all compactions. When compactions run concurrently, they can fetch resources from the pool. And in this pool, we have resources for reads, writes, and we have like, a resource for like abstract CPU pred pool, which currently contains only a single CPU. And CPU here is just like, empty struct. Well, it's not an empty struct, but it is close. So it's not actually like, physical CPU. It's just like logically models that we don't want to oversubscribe CPU. Okay, so let's see how this merge works. Okay, first of all, we do assertions, and we flip the head block we are merging to stage merge. So going back to our ring buffers, we have like level A value block, level B value block, and like the cool thing for level B value block is that it is a single queue, which actually might hold blocks from several tables. We kind of like don't try to really distinguish where one table ends, where one table ends, and another table begins. Okay, so we pick both blocks and we flip their stage to merge. And then we do the actual CPU work. And here, kind of like, on next tick is mostly just to model like this future enhancement where we would have a thread pool here where the work becomes asynchronous. Okay, so let's see the actual compaction. The first thing we do is that we get two slices for things we need to merge. So you see here, we get like values in A, values in B, and then here we'll actually be merging those two slices. So let's put that on the stack and see how we select inputs. And this is like simply like should be relatively straightforward. As usual, let's start with level B because it is simpler, because level A needs to handle a mutable table. Well, before starting, let's actually check the return type. The return type is a tuple of two slices where each slice is optional. Null here means that the table is exhausted. So for level B, if we have a value block, then this block must be in a stage merge, and we slice this whole block. For level A, if it is on disk, it's the same logic. If it is in memory slice, then we just return that slice. Okay, and this is like, let's think about level B. This is a slice of values for the entire block. But, we might have consumed some values from this block before. It is not necessarily like, the first call to merge, because the way it works is like, you read some data from level A, read some data from level B, you merge, and you merge until you exhausted either the chunk of level A or a chunk of level B, and then you refill. So it might be the case that like, you've read the entire block from level A and only like half of a block from level B. So we need to further slice this by what we have consumed. And that is what the position field does. So position tracks the next value, which should get into our merge algorithm. So we slice level B, And for level A, it's kind of like similar, except that there is like a trick. So remember, then we were starting our bar. No, starting our beat commands. We were reserving grid blocks for every block which we might create. And the reasoning here was that, hey, we have a quarter of values we want to process, and essentially dividing that quarter, silly dividing that quarter by the size of a table gives us the number of, by the size of a block, gives us the number of blocks we could create, more or less. But this logic requires that we don't overshoot our quarter too much. And that in turn requires that for and like, okay, it is easy for level B, because for level B, what we feed into a merge is a single block. But when level A is an immutable thing, then the slice actually is much bigger than a single block. The slice for immutable table is sized as the whole table, not as a single block. So if we feed everything here, then we might overshoot. So we slice this from our position from below, but also slice this by value count max from above to make sure that both of the slices are of sufficiently small length. Okay, let's see. Okay, we get our merged inputs. We assert that at least one of them is not null, so they cannot be simultaneously null, because that means that both level A and level B are exhausted, and we explicitly check for that. Okay, and then we check that if it is not null, then it is not empty, but is not larger than the size of a single value block. Okay, that's for input slices. Now, the output slices. The output data lives in table builder in its value block. And some of that is already filled, again, by the previous Tcl merge. Actually, like, remember when I said that, hey, for a merge, we read a chunk from level A, chunk from level B, and then we merge until we've exhausted one of them. It's actually not true, because we have 3 chunks in place. We have chunk from level A, chunk from level B, and also the output chunk. And either of them could get exhausted while we merge. Like, there's like 3 exit conditions. Either level A finished or level B finished. It's like, I mean, not an entire level, a single block. Or actually we've run out of values out. And this actually means that there is a missing assert here, because okay. Because this is actually true here. Values out. Values. Maybe values. Maybe because for output blocks is also actually true that like the output slice must not be empty and it must be not full. Okay. Now we do the actual merge, and there are actually, like, 3 specialized algorithms which go into this 4-pronged if. Okay, so simple case. Values in A is none. So there is nothing from level A we need to merge. And that means that we have to just copy values from level B. So we take our values out, we take our values in, and then we mem copy everything from values in to values out. And we return the number of values we copied. And returning this number of values is actually important for a counter. So you see the like this is like 4-pronged if, but as a result of it, we get, okay, I'm lost. I'm really lost. We get so-called merged results. So no matter in which case we are in, we count how many values we consume from level A, how many values we consume from level B, how many values we have dropped, which means that, like, it was 2 values with equal key, so we took the one from level A rather than and dropped the one from level B, and the amount of values which we emitted. So okay, it was merge. No, it was merge callback. Okay, so if values in is null, then consumed A equal 0, consumed B equals how many we copied, and produced equals how many we copied. Okay, now similar case, values in B equal null. We do exactly the same thing, except that it is now consumed A, which is consumed. But this is a risk. The case compaction dropped tombstone. So what does it mean? It means that you move values from level A to level B, and either level B is the last, and level B is the last level in the LSM tree. So in this case, you actually know that your tombstones do not shadow anything. Like the reason why we add tombstone when we remove a value from LSM tree is so that, like, it like clobbers values with identical key but different value before and says, hey, actually there is no such key. And like, you sync tombstones for the layers. But once you got to the bottom layer, you know that, hey, you actually could drop tombstones. And there is an obvious optimization. Like, you don't necessarily need to get to the lowest layer. You just need to know that there isn't anything below you in the layer. And because in the tables we actually track minimum and maximum key, it could be the case that you could, like, in the middle, you could know that, hey, actually there are no tables from below. So that's why we have these values copy group tombstones. And this is relatively simple. So again, we have values in, values out, values in. Quick tip. Why it is, like, like backwards, why it's like not values out, values in, while it seems that like in out is like more natural order. Well, it is because when you write x equal y, this is like, you copy from the right to the left. And for our memcopy like APIs, we go through that mnemonic. So what we assign to is always on the left, is always first. Okay, so we have 2 indexes, and we iterate while both indexes are smaller than corresponding length, and we pick a value, and if value is a tombstone, then we skip it. Otherwise, we assign it to the corresponding values out. And then we say that, hey, this is the number of values we consumed, which is by how much we advanced the index. This is the number of values we produced, which is how much we advanced the output, and the number of values we dropped, which is the difference between the two. Obviously, this is like somewhat redundant, so we double check that like reasonable identities hold. Okay, let's go back to our merge callback. Okay, and now finally, the interesting results. Values merge. So fully general thing. We have output slice, we have 2 input slices, and we might or might not to drop tombstones. Okay, similarly, we iterate while we have all 3 slices not exhausted. We fetch the values, we compare the values. If it is What? Uh, what what is happening here? Well, okay, yeah, okay, yeah, right. So values are no, this doesn't make sense. This doesn't make sense. Oh, no. This does make sense. So here, like, this is like big value from level A, big value from level B, collapse. Okay, so if value A is less, then we need to pick value from level A. But if this value is a tombstone, and we know that we are, for example, the last level in the LSM tree, then we actually just don't have to write this value, so we are done. Otherwise, we write this value to our output slice and advance the output slice index. For level B, we are not dropping tombstones, so I mean, because like, if we knew that we could drop this tombstone from level B, then we would not have emitted it in the first place. So yeah, here we copy value B. Otherwise, the keys are equal. So we output value A. But if value A turns to be tombstone, and we know that we could drop tombstones, actually it's also like safe to just drop the tombstones. Okay, and then we emit the same statistics. How much we consumed from level A, from level B, how much we dropped, and how much we produced. Okay. So we did our small share of merge, and now we do this tracking. Am I going to commit the comments you wrote, or are they just for stream? Well, I'm definitely going to commit. If I don't forget this, I'm definitely going to commit this assertion because it is available. For commits, well, maybe probably I will. They kind of like feel obvious, but well, if I was well, I guess they're obvious if you're not streaming. But if we are confusing while you are streaming, then probably it makes. I just have case collapse them. Probably it makes sense, especially given like I really like this is my favorite genre, like when you place a command like right after the opening curly brace, it is like the perfect place to write a command in, because well, there is like white space anywhere, like you could add more context there. Okay. Comment from VTwitch. Digging through all these details on the stream seems to have been worth it just for the code improvements. I mean, like, I've spent a whole week, like, disassembling compaction code and like reassembling it again, and like that, scratching my head over the code which got deleted, and like trying to figure out whether, like, it was like genuine dead code or whether I deleted something useful. It's kind of like, it's not. I mean, a lot of work went into this version of the code, even like beyond the stream. So anyway, we are at the merge callback, and now we've like did our merge, and we have our merge results, and now we could advance our positions. So we advance position A, and then we advance position B, and then we advance position in the table builder. Okay. Now. Okay, well, let's skip the counters. Counters I haven't explained, and I will explain them in the end. But the quarters are important. So as a reminder, the quotas thing determines our pacing. Bar is the sum of values in the level A and level B, which we are going to merge for the entire bar. So it's like, it's like our entire work. Then bit is the target for the current bit. And there are like 30, and there are 16 bits at all. So like bit like roughly is bar divided by 16, but that's like adjusted dynamically. And then dan is like how many values we have actually processed here. So actually it feels like this one here should be here. And actually all three. Well, let's do a similar inline for here. And where we view for okay. Value count. We want to assert that that value count is in fact less than value count max. Okay, where was I? Wait, did I? Wait, this is not right. I think I've dropped something. I think I've deleted something important. Let me double check this. Okay, yeah, this one definitely should have stayed the same. So okay, I've merged values. Then I've updated our positions, and then I asserted that positions are all right. Well, okay, and then we have observed our quotas, and actually, okay, so many missing assertions. So quotas done should definitely be less than bar, but what's more, this is crucial, quotas done should be less than equal than quotas bit times quotas bit plus value count bar. So we could overshoot quotas bit, but we shouldn't overshoot it by more than value count max. And that's why like we were like when we were slicing immutable table for the input, we limited from the above. Okay, before we go further, let me explain one thing. I think there was like a question about this, like, 10 streams ago. What is the data plane versus control plane? Because this is like, we've just seen both the data plane and the control plane. This whole like merge thing is like this exact distinction, because you see here, like, like we do like a lot of assertions, and we do like a lot of like redundant tracking, because like this merge result is like necessarily redundant. So, and then like we check it and double check and triple check it. So it feels like, there is like a lot of overhead for fast database. But you see, like all these assertions, we only do them once for the entire chunk of data. And the actual data plane is this values merge functions. So this, like the body of this file, this thing here is the data plane. Operations here we do once for every input values. Outside of this body, all these asserts, we do them once per entire slice. So the costs of these assertions is like 0. On the other hand, this thing here has to be as optimized as possible. Okay. So yeah, Brian, like this is for you. So this is okay. Let me zoom in. Now let me zoom out. So this is control plane. Okay, let's actually do this. So this is control plane. And this is control plane. And this thing here, like this file, is data plane. This is it. This is the whole concept. Control plane is something you do once per many things. And data plane is what you do with each individual thing. Like, I mean, analogy. Let's say you are going to a supermarket and like you have like, a giant bag. So you get to the supermarket with a bag. And then like, you put all those individual items into your bag. And when you put an individual, like, I don't know, fruit or chocolate bar or whatever in your bag, like this is data plane. This is like, your entire food item. But then like, your bag is full. And now like the bag is an abstraction. So you put the entire bag into your car and you don't think that, hey, my bag contains like 100 individual items. No, this is abstraction now. You put bag into the car and you drive the car with a bag. And this is the control plane where like, driving around the city with the bag, you are like in effect transporting individually each grocery item. You transfer individually each piece of bread, each cake, each chocolate bar, each packet of rice or whatever, each individual grain of rice, but you do this on like abstract level. So yeah, this is it. And you see that there is a comment here which explains peculiar way these functions are written. You see, when we look at, for example, merge callback, well, the first argument, merge callback is a bad example because we have like this field parent pointer here. But anyway, it's a merge. The first argument of the merge is compaction. And for merge callback, actually, we get this compaction. And this is a pointer. So this is a pointer to a struct which as fields contains our things. For various copy, various merge, etc., we don't have this first self argument. We only pass in the slices. Why is it the case? Well, because if you pass something by pointer and then you load the fields out of it, optimizer might become confused. So, for example, okay, let's hypothetical. Let's say that we have compaction here, and let's say that, inside our data plane, we also say something like compaction level a position plus equal 1. Well, this might actually be a pretty significant pessimization, because for the optimizer, it is not entirely obvious that nothing else in the code touches this field of a compaction, because this data is by pointer, and actually maybe this data is aliased somewhere. So maybe when we call key from value, it somehow gets a pointer to this compaction, somehow modifies this level A position behind the back. So unless compiler does some kind of super global analysis here, this plus equal 1 here would mean that this value has to be loaded from memory into a register and then stored back into memory every time we do this increment, which would be pretty slow. To avoid possibility of a similar compiler confusion, we just actually say, okay, so we don't pass anything by pointer. There is no anything context. Everything there is here is a local variable. So this index in, index out, they are local variables. And here, when we do plus equal here, compiler can reason that, hey, this variable is never escaped. We never even look at the address of this variable, so it can keep it in the register. Let's reset zoom. And then when we actually need to update our fields, we update fields in bunch. So instead of doing a memory load store for every value, we do it for every batch. And again, it is if we did that direct plus equal 1, it would be valid for compiler to optimize this to this batch operation, where it doesn't load and store from memory every time, but stores the value in the register and then updates it once. But it actually is non-trivial optimization, because you need to reason about aliasing. And here, because this is data plane, we really want to not even think about compiler maybe not optimizing our code. So we write the simplest possible code. It's a little bit of duplication, a little bit of extra logic to manually load our values and then update them. But what we ended up with is a very simple function, which would be very easy to micro-optimize at this stage. Surprisingly, we actually didn't do much of micro-optimizations here, so it would actually be good exercise to get at this function with the benchmarks and profiler and see if some vectorization could be taken advantage of or whatever. Okay, back to merge. So we've updated our values, our positions in value table. And now what we need to do is that, we essentially need to implement the carry flag. So we updated our position in the data block, but it could have been the case that, we've reached the end of a data block. And if that is true, so if this value reaches the position of a data block, then we need to increment our value block. And if that was actually the last value block in the whole table, then we need to go to the next table. We need to increment the index block. This is very similar to how you do add with carry. And this is handled in merge advanced position function. Okay, so let's see what happens here. As usual, let's start from let's start from level B, because level A is more general and level B is common case. Okay, so level B. If we don't have a value block, then our position is already 0 and level B is already exhausted. If we do have our value block and our current position is equal to the number of values in the value block, then we need to do +1. So at this point, we know that, hey, we've fully processed this block. So we go and we pop the block from our queue, we mark it as free, and we release it back to the pool. So okay, we fully merge this block, it's no longer in it. We also increment our position to the next block, and we set reset value back to 0. Now, it could also be the case that our block was actually the last block in the table. As a reminder, we set last block in the table when we read a block. So when we read the block, we get its address and its checksum from the index block. So at this point, we actually know whether there are more blocks in this table after this one. So we set this last block here, specifically so that we could use it here. Because at this point, so you see, like going back to the read value block, if we set this thing, we also immediately release the index block. So at this place, at this point, we actually don't have an index block to just check because we want to release it early. So we just like remember this this flag. Anyway, so it was also the last block in the table. Then we advanced our index block and reset value block. Okay, and release value block. Okay. If we haven't actually finished the value block, then the next merge we do should continue from the same value block. And right now, the stage of value block is merged, so we are actively merging. Here we say, okay, we've done merging this block, and we reset stage black to read value block done. So the lifetime of the block is that first it goes into read value block. This is like active IO. Then it goes into read block done. Then it goes into merge. And from merge, it either goes back into read value block done, like here, or it goes to free, like here. Okay. So this is position for level B. For level A, if it is on disk, then this is like the same copy-pasted code. And again, I really hate it how, like, you know, you have to duplicate this. And for immutable table, we kind of like, there is just one block, and we track this in this extra level A immutable stage thingy. So that's super simple. Okay, so this is level A, this is level B. Now, we also update our quotas. If it turned out that we've actually fulfilled our quota, then we flip compaction stage to beat quota done. But the fact that we fulfilled our quota doesn't mean that we did all the compaction work here. Because remember, our table builder holds index block and value blocks. And to not carry value blocks for every compaction across bit boundaries, we actually want to end a bit of compaction on output an exactly value block. So we might need to proceed a little bit further until the data block is full. So kind of like initially, like, you know, you get here, you flip the stage from bit to bit quota done, and then this is false. And you continue with compaction. And at some point you get back here and you do it again, and maybe, okay, so now this is bit quota done, so it is still bit quota done, but this even still false, and like you go here again. And the third time you actually get to the table builder data block full, in which case you flip to the stage bit table done, and that's the end of it. So after we flipped here, we never ever go back to merge advanced position in this bit. And well, of course, like there is exception. It might be the case that we genuinely, like, we've merged everything and there's still not a full table. So here we also check that it could be the case that we've fulfilled everything. Okay, so that was merge advanced position. And then we go back into our lovely compaction dispatch. Okay, so that was merge. The last thing we do in compaction dispatch, we see if there is a full block in the table builder, and if it is the case, then we go and write it. So we write our either the value block or we write the index block. And both of them are similar. So we now that we know that the block is full, that's actually there is important bit which happens here. So now we know that if the block is full, we actually go and assign a specific grid address for this block. So like this is location. So like we have block in memory, and we now need to write this block to disk. And like we could write it to any free place, and we need to pick one of them. And that's what is done here. And remember, it has like this fancy structure when we reserve stuff in bit commands. So here we reserve blocks, get a grid reservation. We're saying, hey, in this bit, I can like allocate at most like 100 blocks. And here we say, hey, out of my reserved blocks, please allocate one. This is important to ensure determinism. If we are running many compactions in parallel, then all those reservations happen sequentially. And they get deterministic results. So reservations for each compaction are deterministic. Then the order in which compactions allocate blocks between themselves is actually not deterministic. But because each compaction only allocates from its own reservation, the final result is guaranteed to be deterministic. So this is kind of like inconspicuous line, but there's a lot of thought for why it needs to be the case. Anyway, so we get the address, and then we say to the table builder, hey, please table builder, like finish with this block. So fill the hero of the block with his fields, compute the checksum, and produce a block. And then we like go and create the block. And for index table, it is actually exactly the same. And then in the right block, we free the block, release the block, and go back to our compaction dispatch. Okay, so now, this is not all of it, but most of it. So let's go back to advanced position and look at this thing, bit quarter done. So bit quarter done is a stage where we need to do a little bit more of a merging in this bit, but only just enough to fill an outstanding value block. And remember, when we were reading, well, you don't remember that well, I'll remind you, when we were reading value blocks, there was, yes. There was like, this like priority computation. And this is this heuristic. So if we are in bit quarter done, so if this was true, if we've already merged a bunch of values and we need just a little bit more, then we avoid overreading the grid block. Okay, now we have this case, bit table done, which means that here, like the work for bit is actually ended. And if we are in that stage, then actually we run like a separate dispatch loop, which is kind of like similar to this compaction dispatch, but specialized to this end state. So in this state, in like bit table then, we finished our compaction work. We only need to wait for all input output, which is currently in progress, to finish. Namely, at this point, we might be writing some data to disk, and that we should wait until writes are done. And actually, we might still be reading, because remember, like that heuristic we've seen just now with overreads. Like, we kind of like might be pessimistically reading tables from this, but then realize, hey, actually, well, we don't need those tables. So we have to wait for all those writes. And this is exactly what happens here, I think. So if our table builder still has both blocks, then if its data block is empty, we just release it. Otherwise, if we have space for write our output block, we go and write output block. Relatively simple. The same thing goes for index block. Then at this point, if we are still writing something out, we return, because we'll wait until all our outputs are done. Then, assert that table builder definitely doesn't have the value block allocated. And if it still has the index block allocated, then we haven't yet finished the bar, and the index block is full. And this actually pretty tricky. This assert is fancy. So imagine that you finished the bar, you finished the bit, and your index block is full. Well, now actually you could write this index block either in the current bit at the end of it, or at the start of the next bit. Like, there's like genuine non-determinism, and it is important that we actually pick one option and do it. And well, it's simpler to write it as soon as possible. So that's why we do it here in the cert. Okay, and now then we need to just wait until all the other reads are done. So while we have blocks in level A value block, if we are currently reading this block, we just wait. Again, this is sync cancellation. This is fancy. So this is something which would be kind of like easy to get wrong in Rust, which doesn't like naturally supports a sync cancellation. We we cannot just shrug it and just remove this block from the level A value block queue, because this block is being written to by the Linux kernel at the same time. Like logically, this block is in IO ring. So we actually do have to wait until IO ring is done with this block. And once that happens, we go and release this block. Then we do the same for index blocks, and for level B, for index block for value blocks. Actually, this one feels like it could be somewhat simplified. And finally, we call bit complete, where we forfeit our reservation. So we say that, hey, we don't want to allocate anything. Reset all the things, and call the callback, which will go to the forest compaction schedule. Compaction schedule here. So we call compact inspection enter, we pass bit resume callback. So once everything we've seen there is done, we call this callback back. This calls bit resume on the compaction schedule. And here we iterate for all the compactions and find the first compaction which needs to be started. We start it and then return and wait until that compaction in turn returns. And that sort of, I think, the end of the compaction, finally. I guess I just want to wrap it around and look at the things. One thing I want to look at is like how we update the counters. So our quotas track the logical values which are deterministic, which determine when we need to stop our current bits of work. But there is sort of no determinism in the compaction work, because when we read the tables, like there's like a possibility for overread. So like, because let's say you want to produce like one value block of output. That means that you might need to read one value block of input if all those values goes into the output. But it also could be the case that all the values are tombstones and they get dropped. So you might need to read more than one block. So that's why, and how much you need to read, only when you finish merging. So we kind of like optimistically in parallel start reading ahead and we finish when we finished. So counters tracks the actual input output we have done. In is how many values we've read, out is how many values we've written, dropped is how many values we've deleted as a tombstones, and wasted tracks overreads. So let's see how our counters evolve, which should be, and the equation that number of values written is equal to number of values read minus the dropped and wasted values. Let's see how counters evolve. Okay, so at the start of the bit, it could be the case that we are actually at the middle of the table, at the middle of the value block. So on the previous bit, we have a value block with like 1,000 values, and we processed 900 of those values in the last block. So in this block, we have to only process the last 100 values, but we still have to read the entire block in memory. And that means that those 900 values are actually wasted. So here we add those things to wastage. Okay, then this is that winding down phase where we just wait for IO to finish, and obviously all the values from those data blocks are also wasted, so we add wastage here. Except that, like it could be the case that the block is not entirely wasted. It could be the case that we've consumed some value here, and that's why we kind of like say, hey, let's pretend that we wasted the whole block, but then reduce the wastage by the number of values we actually consumed. Okay, then we increment values read every time we read the value block, except that when it is like table immutable. So for table immutable, we increment this like kind of like manually when we do the merge. But also in the merge, we increment the number of values we dropped. And we increment values out when we write value block. And that's it. And this counters field is maintained across the entire bar. So when we assert that counters is consistent at the end of the bar, we actually get a very strong, very strong guarantee that we haven't lost any values in between. I really love this like counters assert. Okay, so that's one thing I wanted to mention. And another thing I wanted to mention is that, like, you see how I like use like ring buffers here, and I really love like the first ring buffer here and the last ring buffer here. Why? Because they are both special cases. They are like generating buffers, but in a different senses. So this ring buffer is backed by an array of equal 1. So actually, this is just an optional. But well, I put this in ring buffer because it is easier. And this one at the end is actually a counter, because you see, as an item in this ring buffer, I use void type. So this is like tuple. Because while blocks are in these ring buffers, they are going to be read afterwards. While in the output block, like like the block wouldn't actually be useful anymore, so no one is going to read it. It is output. So that's why I kind of like don't actually need the blocks themselves, but I want to keep the consistent API. So that's why I put a ring buffer with a void item type here. I'm wondering if that is all about compaction. Well, there is like the bar complete stuff, where we like apply changes to the manifest and whatnot, but that is not really changed since the original. Actually no. There is one last thing. So we have like counters, we have quarters, and here we actually do one more thing. When we apply changes to the manifest, so when we say which tables are added and removed, we once more count of number of values added and number of values removed, and then at the end we kind of like double check that the number of values we removed from the table is equals to like the number of values in minus the number of values wasted, and that the difference between removed and added is number of values dot. So yeah, like check and double check and triple check. Okay, I think you wouldn't believe me, but I think that's really it. That's the last compaction episode, and there's going to be like no more compaction. I think at this point, well, at least at this point, I really understand compaction. This actually feels like it's relatively simple code. It's like just like bar commands, beat commands, then like dispatch loop, then we break out dispatch loop, then we like do beat complete, then we do another beat commands, and we go back in dispatch loop, etc., and then we apply. Yeah, it's easy, but well, actually, well, it's not easy. I'm joking, but it is understandable. Okay, then that's it. No one more compaction episode next week. I hope. That's it for today, and next time we'll, I guess, look at some easy unrelated thing. Targetable probably will go into look at time. Like time is important. How time works, we'll learn next week at 5 p.m. UTC on Thursday, live on Twitch. Or maybe it wouldn't be time. We'll see. Okay, thanks. Thank you very much for joining, for listening. And see you in a week. Goodbye. And let's enjoy our outro track, which is, really awesome.